So welcome back, and this is the last part of this lecture where we'll talk about a few more learning rate schedulers. And so this is the chart for learning rate schemes, right? So you have what we saw earlier was based on epochs where we had step decay. So after one epoch, if something goes wrong, then just decay it, or for every epoch, just exponentially keep decaying the learning rate. Then we have based on validation where we had line search, right? So we were trying multiple learning rates, and then based on which one gives the smallest loss, we were trying to use that as the learning rate. There could also be a log search similar to a line search where you would search for learning rates on a log scale. And then based on gradients, right? These were the adaptive learning rates that we had. So we had Adagrad, RMSProp, Ada Delta, Adam, Adamax. We did NADAM also. We did not do AMS grad, and we did not do Adam W. So these are all the things that we have seen so far. But there are a few more learning rate schedules that we'll see now, which are based on epochs. So one is cyclical epochs, or the number of iterations, right? The other is cosine annealing, warm restart. So these three are what we're going to see now, right? So we'll first talk about this cyclical learning rate. So suppose the loss surface looks like this, right? And for some of you who have exposure to optimization, you would know that this loss surface is what is known as a saddle. So what happens in a saddle shaped loss surface, that if I look it from here, right, then this looks like a minima, right? This point here looks like a minima because it's at the end of the valley, right? But that's clearly not where I want the algorithm to stop, because if I look at it this way, then I could have gone down from here. Oops. Yeah, I could have gone further down from here, right? My minima would have been somewhere down, right? But it's because of this saddle shape where in one direction you are seeing that, okay, I've reached the minima, but there is another direction across which you could have found a better minima, right? And many times, because the deep learning, the loss surfaces that you typically encounter in deep learning are not convex loss functions, it has been observed, and this has been reported in multiple papers, that often when your training is getting stuck or it's slow or something, it's because you're stuck in some saddle point, right, where there is a minima down the valley, but since you are already in this valley here, you're not able to go further down, right? So suppose we initialized the weights to this yellow point, right? This is where you had initialized. Now you're coming down nicely and you'll get stuck in that valley. You'll get stuck somewhere at the red point that I have marked where my mouse is currently, and you will not be able to go down, right? Because our learning rate is decreasing exponentially over iterations. Now, since the learning rate has decreased, so you're going down and you're going on a fast slope, and in most algorithms the learning rate will start decaying, and by the time you reach the valley, the learning rate would have become very small, and now you won't be able to come out of that. You'll be stuck there, right? So now what if we allow the learning rate to increase after some iterations, right? At least there's a chance that it might escape the saddle point, right? And that's what the idea is, that you try to have this adaptive learning rate which will change, but that is often expensive, right? Because you're doing these computations, WT, the history, all of that you are maintaining, then you're doing eta t, eta divided by this history. So you're creating keeping a lot of variables and making things a bit complex, right? And this often happens, right, that the minimizing the loss arises because of this saddle points. So therefore it is beneficial to have these learning rate schemes which could increase the learning rate near the saddle point, right? And adaptive learning rate schemes that we have seen are actually trying to do that, right? They are trying to do that, but as I said, it comes with an additional computational cost. Instead, what if we have a simple learning rate scheme where we alternatively vary the learning rate? So we start with small, go to high, again make it small, again go high, again make it small, just alternatively, cyclically keep doing it. So now we are not looking at history or anything, right? We are gradually increasing it, then again decreasing. So if it's in a high region, it just has to wait out that cycle, and then again the learning rate will start decreasing, right? If it's in a low region, it just has to wait out the cycle and the learning rate will increase and then push it out again, right? There's a very simple schedule that you could use, and this is one such cyclic learning rate, which is the triangular schedule that you could use. And this here mu, which is the period, right? So you could, mu is 20 here, so that is the number of time steps it takes from going to the minimum value to the maximum value, and once it reaches the maximum value, it again goes down, right? So on the x-axis you have the learning rate, and this is the maximum value, which is in this case is 0.5, the minimum value is 0.01, and the value at any time step can be given by this complex equation, but it just looks complex. If you break it down, it's very simple. So let's look at it, right? So if t is equal to 20, I'll just substitute the value t equal to 20 in this equation. Let me just get rid of the annotations. Yeah. So let me just substitute the value t equal to 20. Now I'm going to substitute it here first, right? So when I'm computing this quantity, it's turning out to be t, right? So everything inside the bracket is t. Oops. And now I'm looking at this quantity. So I'd already computed everything inside the bracket, which came out to be 2. I'm in fact looking at this quantity, right? So then this plus 1 from here, and this t by mu, which is 20 by 20. So that quantity comes out to 0 in this case. Then I'm going to look at max of 0. So now I'm looking at this quantity, which is max of 0, comma what I had computed earlier. So this is what I had computed earlier. So that is going to be 1, right? So then I have eta min plus eta max minus eta min, and this entire thing has evaluated to 1. So this is going to be 1, right? So then it's going to be 0.01 plus 0.5 minus 0.01, which is just going to be 0.5, right? And that's exactly what I get at time step t equal to 20. Similarly, you could substitute the value 30 here, and you will get this as the value, right? Somewhere here as the value, right? So that's how you compute the cyclically learning rate. You increase, keep increasing, then again decrease, keep increasing, then again decrease, right? So this is almost like having like a very simplistic idea, right? You are just saying that at some points I want the learning rate to increase, at some points I want the learning rate to decrease, and to make this happen, we had all these complex algorithms which were adapting the learning rate according to when it should increase, when it should decrease. Now this is like a very baseline idea, right? You want it to increase, you want it to decrease, just make it cyclically, and if you are in a bad part, you just have to wait out that cycle, and then again you might, if you want a smaller learning rate, it is going to come in some time steps. If you want a larger learning rate, it's going to come in some time steps. You just have to wait out that cycle, right? So that's the simple idea that you have here. Okay. So now let's see whether this actually solves the problem that we started off, right? So we have this saddle point, and we started with that initialization, and looks like we will get stuck in the valley, right? So I have this exponentially decaying learning rate, which is the black guy, and that comes into the valley and gets stuck there. But this blue guy has a chance because the exponentially decayed learning rate has become very small. But now the blue guy, because it can increase the learning rate at some point, so even though the gradients there are small, when the learning, it just waits till the learning rate increases, and then it gets pushed, and then it comes down into the valley, right? So with this cyclic learning rate, you are able to get out of this saddle point, and saddle points are a big pain, as reported in multiple papers when you are dealing with deep neural networks, right? So this kind of takes care of such bad learning rate schedules, right? Yeah. So now again we are going to use another cyclic learning rate, which is the cosine learning rate. And here, instead of having a fixed learning rate which is 1, we are going to use this cyclic one, and you can see that this algorithm has converged much faster, right? Because it still has some oscillations here, but you could just take care of that by using some kind of an early stopping or something, right? So now let's see what this cosine annealing look like. So let's just see that. So this is what cosine annealing look like. It has a different formula. Again, this is just based on a cosine function. So if you substitute the time step t, the value of t here, right, and your capital T would just be the period of the wave that you have, and if you substitute these values, you will get the effective learning rate, right? And it's better to just show this as the graph, and that you will understand what is happening here. So eta max is the maximum value for the learning rate, eta min is the minimum value, t is the current epoch, and capital T is the restart interval, which is till what time you increase and then again restart, right? So that's what capital T is. And so let's see what happens. So this is what it looks like, right? So you start with a high value and then it keeps decreasing. And when it reaches this interval here is 50. So when it reaches the 50, and you can substitute these values, right? You can substitute 50 here and you substitute 50 and substitute here. So if you compute these values, right? So T mod 50 plus 1 would be 50 mod 51, which is going to be 50, and then divided by 50. So this quantity will just become 1. So you'll have cos of pi, which is going to be minus 1. Cos of pi is going to be minus 1, and then you have 1 minus 1, so this will become 0. So you'll just have the minimum value here, right? And that's exactly what is happening here, right? Okay. And this is called a warm restart, because from once you come to the minimum point, you quickly jump to the maximum point again, as opposed to the triangular learning rate where you are gradually increasing, gradually decreasing. Here you start from a high point, come down, and then quickly go to the maximum value and then again come down. So this is called a warm restart, because when you are restarting, you are not like gradually restarting, but you are starting from a warm point, which is a high learning rate, and then coming down from there, right? So this warm restart is a popular term that you'll hear in many of the modern papers, right? So this is Nmax and min T and the abrupt change after T, which is why it is called the warm restart, right? And there's also warm start, which is quite popular in the transformer literature, and most of the current literature is on transformers. I mean, they're popularly used in many applications. So what happens is that in warm start, you initially let the learning rate increase, right? In all the other algorithms, you start, whatever adaptive algorithms we had seen, you start with some learning rate and then it keeps decaying, right? And even the earlier learning rate schedules that we had said, step decay, exponential decay, you start with some value and there's always a decay there, right? Instead, in warm start, what you do is you let the learning rate gradually increase to the maximum point, and from that point onwards you start the decay, right? So initially, when you don't know much, right, the parameters are all randomly initialized, you're not sure of your gradients, then slowly have the learning rate very small, so that you're not making very large updates. And then as you gain confidence, you keep increasing the learning rate to a high value, and then once you reach a high value, from there on you start decaying it exponentially, right? So this is the default learning rate schedule used in transformer based architectures, and this is what it looks like, right? So as you keep, and if you use different, so the warm up step is the number of steps for which you will let the learning rate to climb. So in one case I have the warm up step as 2000, and in the other case I have the warm up step as 4000. So the 2000 curve of course rises rapidly and then falls, and the 4000 step rises more smoothly and then it falls, right? So starts decaying exponentially from there. Okay, so that's all we had. We covered the different learning rate schedules that we had, and this you could use in conjunction with the optimization algorithms that we have used also, right? So both can be done. So that's all for this lecture, and we'll see you next week again. Thank you.